Hi, today we're going to finish with the SL option D medicinal chemistry. And so the last topic that we want to talk about is the impact of drugs, of the medicines that we use, and their manufacturing and the way that they are delivered on the environment, on the living organisms that are present in the environment. All right. So medical waste includes not only pharmacologically active compounds, PACs, but also the solvents and other byproducts used or formed during the synthesis of those chemicals, and also any kind of contaminated materials that may have come in contact with those particular compounds when the drug was supplied to the patients. All right, so this could be gauze, it could be syringes, etc. All right, now if these materials are improperly disposed, they are going to enter the environment. All right, and they are going to be absorbed by the living organisms in the environment. Now, many of these compounds, as we've been talking about, are relatively non-polar, and non-polar compounds in particular have the problem of being stored in the fatty tissues of living organisms. And so as they build, as these compounds are absorbed, they build up, they are stored, and what we call that is bioaccumulation. All right, now that is what happens in an organism. You just store that, and that's just, every time that you're eating something, you're gonna store some more into you. That's it. That's bioaccumulation. Now, what also happens is that if you are part of a food chain, all right, we are one of the top trophic levels in a food chain. Each level of the food chain is called a trophic level, all right? Well, you're going to get what is called biomagnification. And the reason for that is that lower organisms eat a small amount and maybe have accumulation of, let's say, 1%. But you are a larger organism, you're going to eat a bunch of these little ones, all right? And that 1% may become 5% or may become 10% in your system. So your accumulation is larger. And so going from one step to the other, that's what we call biomagnification. We're going from one trophic level to the next one, all right? And that is really a problem. And this is not only for pharmacological things, but also other types of waste like mercury in fish, all right, or BPCs, all right, which are some type of byproducts of manufacture that have been put into the water systems, all right. But we're going to focus on drugs and medicines, okay. So that's one of the big things that we are concerned about, bioaccumulation and biomagnification. Another thing that we are concerned about, of course, and we already talked a little bit about that when we talked about penicillin and antibiotics, is the buildup of antibiotic resistance, all right? Now, here's the thing. Antibiotic resistance happens as bacteria, all right, build up, evolve, are naturally selected through their mutations, random mutations that they have, but they're naturally selected to resist the particular antibiotics that they are exposed to. And that is because we throw our antibiotics, leftovers, onto the trash. Their antibiotics are overprescribed. We use them to make sure that our chickens and our cows and our pigs are healthier. And we don't realize that by doing that, all right, we are also making it more difficult for us to be able to fight bacteria that may infect us. In addition, even ourselves, even if we are doing everything right, we are not going to consume the antibiotic completely. Some of the antibiotic does not get broken down and we excrete it. All right, and so that's going to go into the water system, that is going to go into the landfills, that's going to go anywhere else, and of course help to build resistance of bacterial strains that will be immune or resistant, I guess, yeah, to the particular antiviral. All right. So what can we do? Well, not much. I mean, we've definitely talked a little bit about that in our penicillin chapter, but we have to be careful with our use. We have to make sure that we're using it completely. We have to make sure that we don't overprescribe it. We have to make sure that we don't ask for an antibiotic when we have a cold, because the antibiotic is not going to do anything. So doctors should test patients before giving an antibiotic. All right, so we know that they do have an actual bacterial infection rather than a viral infection. All right, so that is going to be the most important thing to do in terms of antibiotic resistance. Another thing that we need to be worried about, all right, is nuclear waste. And in this particular technique, we're not talking about, we will have to include a little bit about other types of waste, but we're really going to be talking about nuclear medicine, all right, and the waste that is created when we do radiotherapy, when we are trying to label different things so we can have tracers to figure out how your system is working, when we're doing PET scans, etc., etc. So we use a lot of different radioisotopes in medicine in order to get a diagnosis or to do some treatments. All right, and so the type of effect that this can have is going to depend on several different factors. The half-life, which is how long it takes for half of the sample of that substance to be broken down, to decay into other elements. All right. The solubility. If something is soluble, of course, in water, it's going to be much more dangerous, all right, than if it is insoluble. All right, if it's something that does not dissolve in water readily. The type of radiation, if it's an alpha emitter, a beta emitter, a gamma emitter, a positron, etc., etc. All right, the types of radiation, because alpha emission is very highly ionizing, but it cannot penetrate your skin. But it's a danger if you if it's soluble. You can take it in your water, and then it gets stored in you. If you are inhaling it, all right, because it's become a powder or some type of aerosol, then you can definitely have issues with these alpha emitters. All right. So because ionizing radiation, which nuclear radiation is, can affect and disrupt the bonds in DNA, can disrupt other cells, can kill cells, it is going to be very important that we actually find a good way to dispose of it. All right, and so the way that we do this is we classify radioactive waste into two types: low-level waste and high-level waste, LLW and HLW. All right, now LLW, low-level waste, is a type of waste that we have, but of any material that has come in contact with the radioactive chemicals, drugs, medicines that are being used. Okay, they tend to have low activity, so they do not produce a lot of radiation, and they tend to have relatively short half-lives. All right. So what are we gonna do in this case? All right. So those tend to be easily disposed of. We incinerate them. All right, or they get put into normal landfills. But that's only if the activity is low. For some of the other substances, all right, that have slightly higher activity, all right, or higher, longer half-lives, like the material that has come in contact with cobalt-60. Cobalt-60 is one of the most important radioisotopes used in order to produce radiation therapy, all right, and also cesium-137. Cesium-137 is particularly problematic because it's quite soluble. It's an alkali metal, and you know that all alkali metal salts are soluble. So this is also going to be one of the kind of things that we do not want to just put into a landfill or just incinerate randomly. We actually need to keep those releasing their high energy into what are called cooling ponds. All right, so we have an area where we actually put them to actually absorb that water, absorb that energy, and only when they have decayed to lower levels. So we have to wait a number of half-lives for them to actually decrease in their activity. Then we can dispose of them in ways as incineration or putting into landfill. All right. The water in those cooling points, especially again with cesium 137, is going to be treated in order to make sure that you exchange any ions, any cesium ions that have dissolved into the water are removed, so they are not passed on to other things. All right. The other type of waste that we have is high-level waste. Now, high-level waste does not get generally produced in medical procedures, but in the IB we need to talk about this high-level waste as well, so we're going to go ahead and talk about it. High-level waste is produced in nuclear reactors or in military applications, i.e. creation of weapons. All right, so they have very high radioactivity. All right, they emit a lot. They have very long half-lives. When we talk about very long half-lives, we're talking about 1.3, 1.7 billion years. All right. Some of them are not as long as billions, but some of them will be in the millions of years. So this is not something that we are going to be around to see them decay and become not a problem. And so what must we do in this case? We're going to take this, and normally we're talking about spent fuel rods for nuclear reactors. We're going to take those spent nuclear rods, and they're going to be cooled in water systems. All right, those pools contain boron and other neutron absorbers. All right, then we're going to take those rods and we're going to encase them in ceramic or in glass. All right, the process called vitrification, to actually keep all of that uranium, that plutonium, all of that radioactive material from actually being able to escape. If we put it in ceramic, if we put it in glass, that is going to be insoluble. All right, and so it makes a good case. I don't have a word for it. In order to keep it from escaping into the environment. Then that material is going to be put into metal canisters, which then will be put into caves away from the water tables, away from anything area that may have a seismic material, seismic activity, because we want to make sure that those are undisturbed for the millions or billions of years that they will have to stay there. Those are going to be very dangerous, and if they leak into the water table, they can create a real big problem, because they can contaminate the sources of water that we are going to be using around. All right. Finally, the largest fraction of the waste that comes because of pharmaceuticals, it's not the chemicals themselves, it is the solvents used to make those particular drugs and medicines. All right. One of the things that we use a lot in organic synthesis is chlorinated solvents, which are toxic, and if you incinerate them, you're going to be releasing a lot of chlorine up into the environment, which is bad for the ozone, but it also creates other toxic materials that can be absorbed and are actually even worse than the solvents themselves. And so there is this mentality, this new philosophy that is called green chemistry. And the most important aspect of green chemistry is the idea of atom economy. All right. Now, atom economy is how to be efficient in your synthesis. So if you want to make a compound and it has a particular molar mass, all right, atom economy would encourage you to make that percentage, what percentage of that mass is of the total number of mass of all the different reactants that you have used. All right, that fraction, you want it to be high. So you want to minimize the number of steps and the number of different reactants and additives and blockers, etc., that you are going to be using, so you can have most of the material that you're using go to your final product rather than stay as just a portion. All right. So what are the principles of green chemistry? You do not need to memorize all 12 principles, but getting a general idea of what they are is a good thing. Okay. So obviously, principle number 1 is to do prevention. So to basically try to avoid creating waste. All right. Rather than so it's easier to avoid creating waste rather than having to clean it up, having to treat it. So think about how you're going to do your synthesis. Atom economy, again, maximize the use of the materials so very little waste or byproducts are made, and most of the mass of what you're doing is going directly into your products. Therefore, you have to make less toxic materials. All right. 3 is use less hazardous, less toxic chemical synthesis. So try whenever possible to use materials that are less toxic. So replace some of those chlorinated solvents for non-chlorinated solvents, even if it may mean that you have to take a little bit longer to do the process. All right. Design your chemical itself to be less toxic. All right. So there are different ways you can have the same functionality without necessarily having chlorine, without necessarily having something that will break down and attack your DNA, etc., etc. All right. Again, some of these ones are they come together with it. Use safer solvents, use safer auxiliaries. All right. So substances that you can add to it in order to create or allow for a reaction to take place in one way. That's definitely something that we can do. Try to make sure that you're being energy efficient. So reactions that don't require high pressure, they don't require high temperature. Use of renewable livestock feedstocks. That means actually, can you take advantage and have bacteria? Can you have plants make some of these materials for you, so you can actually reuse them? All right. So you can, or you can use the plants to actually make them for you. So it's going to be easier, or the bacteria making them, or the fungus making it for you. So you actually don't have to do all this toxic parts. It's actually much easier. Plants, bacteria, fungi are so much more efficient than we are. All right. Reduce derivatives. All right. So if you can actually keep it to be just one particular compound rather than having to put different groups on it and try to modify it too much, that's actually going to be easier. Use of catalysts. All right. Catalysts will make a reaction happen multiple times as well, rather than having to do stoichiometric amounts. So if you need to have 1-to-1, that's not great. If you can have 1 and it can produce 10, 30, 40, 100 times that reaction, that's much better. All right. An important factor here is number 10. The design of the chemicals should be so they degrade. And this is not only for medicine, but for many other things. We are now starting to develop our plastics so they will biodegrade eventually. It's still not great, not there yet, but we are moving in the right direction. All right. Obviously, check for pollution. All right. So this is something that should be done as you're synthesizing. This is not something that you should be checking afterwards, but in fact, as the process is happening, be taking this. And obviously, just make sure that you do safer chemistry so you are avoiding any kind of accidents. All right. Releases, even if there is an accident, you want to make sure that your chemicals should not be so toxic that they're going to be a problem. All right. So thank you so much, and we will continue with a higher level a little bit later. Thank you.